We're looking at an example on book prices. You and another student are given the task of determining if books differ in cost through Amazon and a local bookstore. The other student gathers data by selecting a random sample of 8 books from Amazon and then a second independent random sample of 8 books from the local bookstore. We have the data below along with the summary stats. So based on this data collected by the other student, we want to know if there's significant difference in the cost of books for the two places. So I've already filled this in so we can run through it quickly because this was the topic of what we did in 6.4. If we have two independent samples, our null hypothesis is that the difference in the two population means is 0, or the means are the same. Here we're looking at a difference, and so our alternative is not equal to 0. Our test set then is the difference in the two sample means, which we were provided, divided by the square root of the s's squared over the sample sizes, and each of the sample sizes here is 8. So the numerator of the test stat is negative 2.5, and I did the denominator separately because we're going to talk about that value in a little bit, which was 14.32. The number we're dividing by is called the standard error. When we divide, we get a test statistic of negative 0.175, which is a pretty small value. Degrees of freedom being the smaller of n1 minus 1 and n2 minus 1 would be 7, since we're both 8, and we are assuming we have normal populations here because we have two small sample sizes. So if you go to StatKey with the t-distribution and degrees of freedom 7, and you look up negative 0.175, you'll get that each of the tail areas is 0.433, so doubling that gives 0.866. That's a very large p-value, which would lead us to a conclusion of failing to reject the null, and we would say that we do not have significant evidence of a difference in the population mean book costs for Amazon versus the local bookstore. So now we're asked, how might we have conducted this study instead, and why would that be considered advantageous in this case? So this student took two separate samples of books, one from Amazon, one from the bookstore. Instead of taking two independent samples of books, what we could do is take a single sample of 8 books and look at the same 8 books at Amazon and the bookstore. So what we would have here really is a single sample of size n equal 8, and we're checking that book both places. Those would not be independent. If I'm looking at the same book in two places, the cost should be similar in the two places. Why would that be advantageous here? So notice that our standard deviations, S1 and S2 from our original data, is pretty large. So what that is producing is a fairly small or a fairly large value in the denominator part here, that 14.32. So S1 and S2 are large. Why are they large? That's because there's lots of variability in book prices. When you have data that has a lot of variability inherent in it, like book prices, which can range from just, $5 to hundreds of dollars, what we can have happen is that we're not actually able to detect a difference when we're looking at this independent sample type case. So suppose that we do this paired data type structure instead. You collect the data from the study design we just mentioned. And so now when we look at these values for Amazon and the bookstore, they're paired up. These are the same exact book. Now the question is, do we have a difference in the costs for the two places? Does our conclusion differ from part A, and what accounted for the difference? And we can look at the standard error for both of them. So when dealing with this, which is really the new stuff here in 6.5, when you have paired data, the first thing you want to do is look at the difference in the two values. We'll call that D, and you can subtract either way you want. I'm going to do Amazon minus bookstore. So we would take 53 minus 63 and say we just have a difference of negative 10. 81 minus 89 produces a difference of negative 8. This one's negative 3. This is negative 6, negative 12, and so on. This one's a positive 3, and these are both negative. Now we don't actually care about that raw data anymore. This is the data we're going to work with. So from this data, we have a sample of size 8. Our mean, which we'll call X bar sub D to denote we're doing difference data, for those 8 values is negative 5.5. And if you plug that in your calculator, you would also get a standard deviation of 4.928. And I'll subscript the N with the D as well. So what we would look at for our test here is that the population mean difference is 0. That would mean if I looked at all the books sold by Amazon and also the bookstore, and I looked at their differences, that on average it's 0. That suggests there is no difference in the costs in the two places. Since we were doing a two-tail, just wondering if there's a difference, we would do mu sub D not equal to 0. This is assuming then that our differences come from a normal population. So assuming difference data is normal because of the fact we have this small sample. So what our test stat will be is our sample value, and it's really technically then minus the test value of 0, but just our sample value, over the standard deviation over the square root of n. And this produces a test stat of negative 3.157. Degrees of freedom will be the n minus 1, so 7. And so if you go into StatKey and you enter a degrees of freedom of 7 and you look at a two-tailed test with a negative 3.157, you'll get 2 times 0.008 or 0.016. This time, this is a small p-value. So in this case, we would reject the null and find that we do have evidence of a difference in the population mean book prices for the two locations. Does this conclusion differ? So this does differ from part A. And the question is why? So as we noted before, we had large standard deviations producing that big value down here in the denominator, which produces a really small test stat and therefore a big p-value. What we've done by pairing the data is we've reduced the variability we're seeing. Now, if you look at the standard deviation that we're dealing with, it's a lot smaller than our original standard deviations. We have a 4.928. So if you look at the denominator in the second case, this piece down at the bottom here is just 1.742. So when I'm dividing by that smaller standard error, I'm producing a larger test stat and therefore a smaller p-value, and I am detecting the difference. So in cases like this where you have data that's very variable from data point to data point, so book prices can differ a lot, using this paired structure can produce differences without a lot of variability and actually allow you to detect a difference if one does exist.